Welcome to the Human 5.0 Project, the podcast where we cut straight to the breakthroughs that matter, the show where science meets self-optimization. I'm your host, Ultimate Biohacker 10X, and here we break down the real research, real data, and real dosing behind modern biohacking, from compounds and peptides to techniques, devices, lifestyle strategies, and performance protocols. Most people jump in and jump out before they get the gold, so we're keeping it tight and delivering the essential insights you need without the fluff. If you've taken the time to hit play, we'll make sure you walk away with valuable knowledge that can transform your approach to longevity, health optimization, and beyond.
Hey loyalists, biohackers, and regen rebels, this is Ultimate Biohacker 10X back on the lanai under a crisp Florida morning sky. If you've been tracking our recent deep dives on exosomes, MSC therapies, and the limits of paracrine medicine, today's episode is the next logical step. Because the question becomes, what if signaling isn't enough? What if calming inflammation isn't the end game? What if we could actually replace damaged tissue safely? Today, we're unpacking one of the quietest but most profound revolutions in regenerative medicine, MUSE cells, multilineage-differentiating stress-enduring cells. These are endogenous, non-tumorigenic, pluripotent-like repair cells discovered by Mari Dezawa in Japan. Not reprogrammed, not genetically altered, not embryonic. They already live inside you, and in 2026, they may be the first stem cell-derived therapy that actually lives up to the promise. Quick disclaimer before we go further. This episode is educational only and not medical advice. MUSE-based therapies are investigational and available only through regulated clinical pathways. Always consult a qualified physician. Let's get into it. No one expected the MUSE story, which began at Tohoku University around 2010, but the roots go back even earlier. Around 2007, Professor Dezawa's lab was studying how mesenchymal stromal cells survive stress, hypoxia, nutrient deprivation, enzymatic damage. Most cells died, but a tiny fraction survived. And not only survived, they did something strange. They formed clusters resembling embryonic stem cells. They differentiated into ectoderm, mesoderm, and endoderm lineages. And they did it without reprogramming. That fraction turned out to be 1 to 7% of MSCs, marked by SSEA3, a pluripotency-associated surface antigen. These cells were naturally occurring, stress-enduring, differentiation-capable, and critically, non-tumorigenic. They were named MUSE cells for exactly what they do best: survive stress and repair damage. They've since been identified in bone marrow, adipose tissue, dermis, peripheral blood, umbilical cord tissue. This isn't engineered therapy. This is your body's built-in emergency repair crew. Let's do some comparisons here. Embryonic stem cells and iPSCs are powerful but have tumor risk. There are ethical and regulatory landmines. Traditional mesenchymal stem cells are safe but mostly act via paracrine signaling. They calm inflammation but rarely become new tissue. Exosomes lead to even more refined signaling, and they're excellent for immune modulation, angiogenesis, and recovery. But they're acellular. No integration, no long-term replacement. Now enter MUSE cells. They sit in a unique middle ground, pluripotent-like but non-tumorigenic, low telomerase activity, no teratoma formation in long-term studies. But here's the real differentiator: homing and integration. When injected intravenously, MUSE cells sense injury signals like sphingosine-1 phosphate, or S1P. They migrate to damaged tissue. They cross the blood-brain barrier. They integrate into host tissue, differentiate on-site into functional cells. There's no HLA matching. There's no immunosuppression. They don't just signal repair, they become the repair. Recent 2024-2025 research even shows macrophage-like behavior, phagocytosing debris, modulating immune responses, cleaning up the injury environment before rebuilding. This is why MUSE cells just aren't better MSCs. They're an entirely different class of regenerative biology. Japan is leading the charge. Through the Life Science Institute, part of Mitsubishi Chemical Holdings, Dezawa's team developed CL2020, an allogenic MUSE cell product. As of 2026, multiple phase 1 and 2 trials are completed or ongoing. There's an excellent safety profile, no tumor formation, no serious adverse events, durable functional outcomes. Key indications studied: stroke or subacute ischemic stroke. In a double-blind randomized controlled trial, there was significant functional recovery, which led to sustained improvements out to 52 weeks. Acute myocardial infarction led to improved ejection fraction and reduced infarct size. ALS phase 2 data showed slowed disease progression, which was safe with repeat dosing. Spinal cord injury led to functional gains and strong tolerability. Epidermolysis bullosa showed skin integration and collagen production. Neonatal hypoxic ischemic encephalopathy showed 66% achieved normal developmental scores, and more trials are underway for ARDS and inflammatory organ damage. There are no phase 3 approvals yet, but 2026 to 2028 is the inflection window. You can count on that. So where are we going? Here's the honest framing. Exosomes are phenomenal support tools. MSCs are excellent immune modulators, but MUSE cells are true rebuilders. They offer off-the-shelf allogenic use, IV administration, injury-specific homing, actual tissue replacement. Long-term integration challenges remain. MUSE cells are rare, so they need expansion. Manufacturing scale is complex. Large phase 3 data is still pending. But if outcomes hold, MUSE cells just don't complement regenerative medicine. They redefine it. And interestingly, the future may not be either or. Exosomes may prepare the environment. MUSE cells may finish the job. MUSE cells are not hype. They're what happens when biology solves the problem itself. Discovered through stress, activated by damage, designed for repair. From Professor Mari Dezawa's persistence to real human trials, MUSE cells may finally bridge the gap that exosomes and MSCs couldn't fully cross. True regeneration, without tumor risk, and without genetic manipulation. Stay endogenous, stay stress-enduring, stay unbreakable, and there's going to be a whole lot more. You just wait. Thanks for listening to the Human 5.0 Project.
If you found value in today's episode, share it with someone who's ready to elevate their biology. Make sure to follow the show for weekly deep dives into peptides, protocols, devices, lifestyle strategies, and the science of high-performance longevity. Until next time, stay curious, stay optimized, and stay 10x.